All right, so now that we've established some basis of how light interacts with semiconductors, let's look at the simplest kinds of devices that can be made, the simplest types of optoelectronic devices that can be made. So the general class is called photodetectors. Now the first photodetectors ever were actually photoconductors, and you might still see them called photocells, and it's the kind of device that's used on the lights. If you have outdoor motion sensor lights, there's a photocell which tells the device whether it's night or daytime, and so it can only turn on when it's dark. So a photoconductor is essentially a slab of semiconductor. Let's say that it's N-type doped. And you put two contacts on it, and then it's set up so that the leakage current through here is rather small, but it will always be there. But then when light shines on it, you start to get electron-hole pairs and photoexcitation of electron-hole pairs. And so you can measure the current in the dark and the current in the light, and as long as the current is bigger than the dark current, you'll have the photoconductive gain. So why does this happen? Well, we have to look at the expression for conductivity, which is going to be given by E times N times mu sub N plus E times P times mu P. So in the dark, we only care about the majority carriers. So only this term is present. Now in the light, both terms are going to survive. And we have to remember, let me just write this out, that each of these terms, N and P, can be broken out into N naught plus delta N for this one, and P naught plus delta P for this one. What we're saying here is that the P naught term is essentially negligible, but for usual low injection conditions, this delta P can start to get quite a bit larger and make P appreciable compared to N itself. So for usual low injection conditions, we would assume that N naught is greater than delta N, so we could kill this term, and then delta P bigger than P naught, so we could write this more like this. And so subtracting these two things, we get the E surviving. This part subtracts off. Delta P times mu P survives. So the change in the photocurrent is governed essentially by the light injection level and then the mobility of the minority carriers. So those are the first detectors made. And then the next type involves diodes. So let's look quickly at the JV curve for a diode and take an overview of the different regimes of operation. So we have amps per centimeter squared and voltage in volts. So the diode's IV curve looks like this, and we can define 4 quadrants of operation. Now, when light shines on a diode, a semiconductor diode, and is absorbed, creating a light or photocurrent, what we can envision this doing is shifting this curve downwards like this. So it's, in the ideal case, it stays parallel. Oh, I should just like. So this is in the dark, and this is in the light. So the difference here is the photoinduced current, which we'll discuss in a minute. So we can classify the types of devices that operate in these different regimes. So up here in the quadrant 1, we have LEDs and lasers. And in this quadrant, we're putting in electrical power in forward bias, and we're getting out light power, or the extraction of photons. Region 2 doesn't matter, the curve never goes there. Region 3 is important, though, for photodetectors, especially photodiodes. So this means that we run most photodiodes in reverse bias and measure a linearly proportional response to the light-induced current. The number of photons creating current actually is proportional to this shift. And then in the 4th quadrant, we have photovoltaics, or solar cells. So again, in this quadrant, under reverse bias and current flowing that's induced by the light, it means we're actually expending energy here. But in the 4th quadrant, we have this unique effect of power generation. We actually have the device generating power instead of consuming power. So let's start here with photodiodes and then work our way through these other types of devices in subsequent chapters. So when we looked at the photoconductor, it's really a mixed minority and majority carrier device. Now let's look at a photodetector, which uses the p-n junction as its basis. So let's draw our same old picture of a p-n junction schematically from the side, showing the 3 regions. The P, Q, and R, quasi-neutral region, the N, Q, N, R, and then depletion width. So now we're going to imagine superimposing some light on this structure, and we're going to imagine it coming in from the side, although the geometry could be varied. So the light is going to come in like this and be absorbed starting from the surface according to the Beer-Lambert law. And in each region, some photogenerated carriers will be created. Now, looking on the band diagram, we can see that there's a good chance that photocarriers made within the depletion width will be separated and collected at the outside contacts out here at the left and right. So photogeneration here gives you an electron hole pair, but they're inside a very strong E field, and so they're swept out very quickly, like so. So a usual assumption is that the collection efficiency inside the depletion width should be unity or 1. Now we have to think about what happens in the quasi-neutral regions, in the p-type and n-type quasi-neutral regions. So what we have to look at here is the full ambipolar transport equation, and then simplifying it to low injection conditions. And it turns out, in the end, we can write the equation in the quasi-neutral regions as d delta n dx squared, d squared minus delta n over L sub n equals 0. So it reduces down to this form that we used previously for the recombination, the recombination currents in the quasi-neutral regions under forward injection, forward bias, or minority carrier injection when we were deriving the ideal current of a PN junction diode. But in this case, what we're going to use as the source of this current is that fraction of light which comes here. So a nice way to look at this is to create a function which tells you how much photocurrent will be collected, or a collection efficiency function. So if we have this at 1 or 100% collection, representing the depletion width, we can then look at the collection efficiency in both of the quasi-neutral regions. And these will decay from 1 as e to the minus distance, let's call that x, over the minority carrier diffusion length in that region. So similarly over here, for the electrons in the p-type quasi-neutral region and the holes in the n-type one. This is a useful concept because we can just multiply this by the carrier generation function. So we can convert Beer's law into a generation rate by saying, I equals I naught x to the minus alpha x. And what we're actually going to look at, this describes the power which is still contained in the propagating beam of photons. What we actually want to look at is those that are no longer with the others propagating, so those that are taken out of the beam. So what we have to look at is actually di by dx. And so we get an I naught, we pull down a minus alpha, and then we have x to the minus alpha x. And then we define this as our g. Now this intensity here, this would be watts per meter squared. And we have to convert that into a photon flux so that we can get the generation rate of electrons and holes. So we can remember that each photon has h nu of energy, and convert watts into number of photons by saying that if they were all identical photons, let's say it was a red laser, the number of photons per meter squared per second times the energy per photon gives us the right units. So we can get our g here, and then substitute in this function as a function of distance, and we'll have g naught at the maximum point at the interface, and then a decay like so, which decays as x to the minus alpha x. So if we multiply these two things together, I'll call this my collection function of distance x. So I'm just going to sort of do this schematically. My collection function of x times my generation rate of x dx. That will give me my overall current from the diode this way. Once I know the current from the diode, I can go back on and superimpose it on this IV curve that we drew before. So this is none other than the J light here. So this formalism holds for any device that's operating based on a p-n junction. So both simple photodetectors as well as photovoltaics or solar cells can use this same formalism to figure out how much current is collected as a function of bias. And of course, as you apply different biases, the depletion width will either shrink or expand, just as we've discussed previously in terms of reverse bias expanding the depletion width, for example. So if we want to maximize the current or the signal that we're getting from our photodiode here in this third quadrant, our goal would then be to maximize the amount of current that we get in the light. So as we can see, we're losing some current here in the front of the device where the P quasi-neutral region exists, as well as in the back in the N quasi-neutral region. So we can do a few things from a design point of view and operation point of view. The first thing is, as we alluded to a minute ago, what if we apply a large reverse bias such that the depletion width expands? So now we'll make our depletion width bigger, and then we'll have the same kinds of decays going out in each direction. This becomes hard to do because you can never, it takes a lot of voltage to move the depletion width appreciable distances. So what you'll end up doing is eventually applying enough reverse bias that you would start to have a large dark current, and thus the detectivity of the diode would go down because you'd have a large background current. So the other thing you could do is make the p-type region thin and very heavily doped so that you have a short diode on this side, and then make a very large minority carrier diffusion length in the rest of the device. That would help you pick up more current. A third thing you can do is make a diode that can operate in very small bias, but still have a large or larger built-in field. So this is called the PIN device, and that stands for P intrinsic N-type. So here we put in P plus material, intrinsic material, and N plus material. And an interesting thing happens now. If this is truly intrinsic, meaning that there's no acceptors or donors whatsoever, that means that it's impossible to build up space charge. And if you have no space charge, it means that the bands must be linear versus distance instead of parabolic, like we've usually seen for normal doped junctions. So the band diagram looks something like this then. So the p-type region and n-type regions are connected like so with linear bands. Now, you can certainly bias these additionally, but already if you have a built-in voltage here, because these are P and N plus, the V built in is kind of by definition E gap. And so the E field here in magnitude is going to be equal to E gap over the thickness from here to here. So essentially you can make the entire volume of the diode have an electric field of a certain value that you can design by manipulating the thickness and the doping. So the collection function for this diode, a PIN diode, would look something much more like this from front to back. Basically 1 everywhere, and then in these very thin P plus and N plus regions, you'd start to see a drop-off. But especially if those are kept thin, the entire volume can be used to collect almost 100% charge, especially under additional reverse bias. The challenge is making the intrinsic material. So silicon, we can do this pretty well by purification. Other materials like 3,5s require very good epitaxial growth. And the last thing you have to think about is additional dark current being generated from traps inside the depletion width. So if there are defect states coming from impurities or bad crystal growth, those can add to the dark current and thus reduce the signal-to-noise ratio for your light current. Now the last and very interesting type of photodetector I want to just touch on is called an avalanche photodetector, or APD. Sometimes it's also said the avalanche photodiode. Now the idea here is that you create a band structure and a bias condition such that you're just on the verge of reverse bias breakdown. So this requires some careful design of the material and layers. Let's just assume then that you have the bias condition such that neither electrons nor holes that are thermally generated inside the depletion width will cause reverse bias breakdown. So here we're talking about in the dark, the part of the avalanche breakdown here. So our operating point is set here before this happens. Now, what you see, which is really cool, is that if you come in with a photon and generate an electron-hole pair here, the fact that now there's more minority and majority carriers around in this very large electric field region means that some of these carriers on their way out will actually generate extra electron-hole pairs and get this avalanche multiplication. So the extra current that's flowing through the diode in the light actually pushes it over the threshold for avalanche multiplication, and we get that first electron-hole pair generating a second, and then those generating a third, and so on and so forth, so that by the time the current is extracted from the diode, we get an exponentially larger current. Now this is important because in all of the detectors that we discussed so far, we had this J light, right? This J light was linearly proportional to the photon flux. So one photon generated one electron-hole pair, and thus the current is the maximum light current for those devices, even if they had 100% collection efficiency, would be exactly equal to the photon flux So quantum mechanically, you get a one-to-one relationship between the number of photons and the number of electrons, and thus the current coming out. Now in the APD, or the avalanche photodetector, you get this gain factor, which is huge. It's exponentially bigger. And so the APDs can actually be used to detect single photons. So this is the electronic analog of photomultiplier tubes, which used to operate by using an avalanche of photoelectrons emitted from a metal in very, very large fields. But we can do this compactly in a small semiconductor chip now. So in any case, for the APD, the current looks something more like this. It will exponentially take off for even single photons hitting the detector. So then the next thing that you have to do to use these effectively is to actually quench that cascade, because what it means is once that multiplication cascade starts, it takes off on its own and has a very high current state until something changes. And what needs to change is that the voltage needs to be turned back down to quench that cascade after a single photon hits. And in this way, you can actually count single photons. Now, in the steady state case, you can still use the APD as a very sensitive detector for low light conditions. You just have to make sure that the current running through the device is below the damage threshold for the device so that you don't burn it out. So never expose your APDs to room light when they're under bias.